Hello students, welcome back to the third video where we will be doing few examples related to the concepts which we have already learned in part 1 and part 2. The question goes like this: a black body of radius 3 cm can be considered to be a perfect black body radiator if the temperature of the ball is 600 K. Calculate. They are asking A, B, C and D. Step by step let us calculate. A part is the peak wavelength of the spectrum of electromagnetic radiation emitted. Going back to the concepts which we have already learned, Wien's displacement over here, it relates lambda maximum with the temperature. So using the same concept, we just plug in the values, we get the answer. Lambda max, again I repeat over here, it is not the maximum wavelength, but it is the wavelength at which the intensity is maximum. So lambda max into temperature, they have given 600 K. You plug in the value and calculate lambda max with this constant 2.9 into 10 to the power minus 3. This formula is there in our formula booklet. We just have to plug in the values. B part is the power per unit area emitted. Power per unit area over here is equal to sigma T raised to the power 4. So we plug in all the values. Sigma is Stephen-Boltzmann constant. 0.67 into 10 to the power minus 8. Temperature is 600 Kelvin raised to the power 4. We get power per unit area which is radiated from the black body will be 7348 watt per meter square. C part is the total power emitted from the ball. Ball is very small, it is just a 3 cm ball. So total power will be equal to power into the area, the surface area of the ball, which is equal to 4 pi r square. R is in centimeter over here. We need to convert that into meter. So 0.03 square, which is giving me 83 watt. And the last part, D, is the intensity. Intensity means, let us understand this problem. This is the source. It is radiating the radiations. The intensity which is maximum for this very particular wavelength, lambda max, is 4.8 into 10 to the power minus 6. These radiations are received at a distance of 1 meter from the source. What will be the intensity of the radiations received is part D. So I is equal to P over 4 pi r square. Over here R will be the distance. Plug in the values. Answer we are getting is 6.6 watts per meter square. Coming back to next question. Applying the same concepts on astrophysics parameters. It says a star Betelgeuse has a radius of 3.1 into 10 to the power 11 meter and a surface temperature of 2800 Kelvin. Find its luminosity. Before proceeding, let us come back to our concept. In case of stars, luminosity is power, and power we know is this. Power is equal to sigma T raised to the power 4 into A. Using this concept over here, luminosity is power in case of stars, which is equal to sigma A T raised to the power 4. Sigma is Stephen-Boltzmann constant, 5.67 into 10 to the power minus 8. Area is 4 pi r square. R they have given over here, and T also they have given. So just plug in the values and calculator will give the answer 4.2 into 10 to the power 30, a really high value of power which is radiated from the star. Second example, the luminosity of the sun is 3.89 into 10 to the power 26 watts and its distance from the earth is 1.5 into 10 to the power 11. Calculate the apparent brightness. Again, let us refresh what we have learned. In case of stars, intensity is referred to as brightness B. This intensity is referred to as brightness B, and luminosity is this power P. So L, luminosity, is the power. B is equal to the intensity I, which is equal to power over area. So luminosity is power, which is equal to 3.89 into 10 to the power 26 over area is 4 pi r square. Over here, whenever we are dealing with intensity or brightness, it is the distance between the source and the receiver. So here source is the sun, receiver is the earth, and the distance between them is 1.5 into 10 to the power 11. So plugging that as 4 pi r square and calculating, I am getting the apparent brightness is 1375 watts per meter square. I hope this was easy and you were able to understand this. Thank you for watching the video.